So there's a few memory tips we can use when we're trying to remember our reaction pathways. I'm going to go through the major reactants that we start with in terms of reaction pathways and look at it that way. So the first one is to start with our haloalkanes, because haloalkanes and alkenes are the two things that most things are actually able to be made from. So haloalkanes require heat and reflux for every single one of their reactions. So if you remember haloalkane, heat and reflux, so H and H. They can either go through substitution reactions or elimination reactions. In the substitution, we're changing this halide into a new functional group. So we're substituting out. So we need to remove the halide and react it with a compound that actually has the functional group that we want. Whereas in an elimination reaction, we're actually removing the halide and replacing it with a double bond. So we're actually removing a halide and a H and forming a double bond. So when we go through with and I'm representing this as the organic group, this is our halide. So we're replacing this halide with either a nitrile, which is our C triple bond N, an hydroxyl or to make an alcohol, which is our OH, our amine with an amine functional group, or we can make an alkane with an elimination reaction. So you notice here, to help you try and remember, I've actually said what we want is the CN, which we get from our potassium cyanide, and this is our CN group. So if you remember that I want a CN, I can react it with a salt that has a CN, and it's the K. You can look at your polyatomic ions to know that CN's 1, so it's going to be K, just one potassium. If I want my alcohol, I need to add something with an alcohol in it to substitute that functional group. So sodium hydroxide, or a strong hydroxide, we need that to be aqueous, so, and I'll go through that in a second. Our amine, we need to add something with an amine, and the most common one is adding ammonia, which is basically our HNH2, and we do that in dissolved in ethanol. And we'll notice here we're still doing the sodium hydroxide for both, but the difference here is in terms of if I want to make an alcohol, I actually add it in water and an aqueous dissolved, so it's a dilute sodium hydroxide. Whereas with my alkene, I don't want to have any extra water in here because that will make my alcohol, so I do it in ethanol. So a memory tool to help you with your conditions is that for all of them, except when I want to make an alcohol, I dissolve in ethanol. With an alcohol, the memory to remember that to make the alcohol it's dissolved in water is the ROH looks a bit like when I write H2O out as HOH. So dissolve the NaOH in water. So ROH dissolve in water because it looks like water, HOH. So our next group to look at are our alkenes, and they go through addition reactions. So if you're trying to remember the type of reaction, think about A for alkene, A for addition. In this one, we're adding a reactant and we're breaking that double bond, and the reactant will actually then bond with the two carbons on either side of that bond, one part on one and the other on the other. So whatever we want in terms of our desired product is what we're going to need to add to be able to have those things in it. So for a haloalkane, what we're doing is we want the halide, so we'll need to add, if we just want a single halide, just a haloalkane, we have to add the alkane, but we also need to add a hydrogen because we need to have two atoms, one to bond to one carbon and one to the other. So we'll add a halohalide. With our dihaloalkane, where we actually have two of our halides bonded to the two carbons, we need to add the element of the halides. Remember, all of our halides are diatomic elements, and we don't need anything extra because our halides are really reactive and they've got a double bond available, which needs slightly less activation energy to break that. So then we don't need to add anything else other than the hydrohalide or the halide. We do need to remember, I'll come back to Markanov's rule, but we do need to remember the Markanov's rule for two of our compounds in terms of what we're adding. So these are our halides. So remember, halides reactive, so nothing extra. Whereas with our alkanes, our alcohols, and our polymers, we need to add a catalyst because we need to lower that activation energy to be able to help break that bond. So all of them require a form of catalyst. So if we're trying to make an alkane from an alkene, we add hydrogen because what we're trying to do is create an alkane with saturation. So we need to add some hydrogens. So with that, we'll need a metal catalyst, and the commonly used ones are palladium, platinum, and nickel. If I want to make an alcohol, I need to have this OH, but remember I've also got on that other carbon another hydrogen. So on one carbon we'll have the OH bond and the other one is a hydrogen. So in this case we're adding our HOH, which is our water, and in this case we need our strong acid catalyst in terms of this one, but we'll also need heat and pressure. With a polymer, we're adding lots of the alkenes together to polymerize to form our long chain. We need that catalyst, we need heat and pressure. And you notice here, as soon as I start getting above just the two atoms, our diatomics, so our two atom thing, so a hydrohalide, a halide that's in its elemental form, or hydrogen, as soon as I get beyond 2, I need to have heat and pressure as well, because that also provides the energy required in terms of the activation process. So our Markonov's rule, notice here for our halides and our hydrogen, they're the same. So it doesn't really matter, there's no difference. It's going to be X and X, or it's going to be H and H. But in terms of where I've got two different things that I'm adding across the carbons, hydrogen is really attracted to other hydrogens. So the hydrogen of what we're adding is going to go to the carbon that had the most hydrogen initially. So the hydrogen is going to bond to this carbon. So we'll get our hydrogen bonded here. And our other thing, so our halide, or the OH for our water, will bond to the carbon that had the least number of hydrogens. So we can see here I had 2 hydrogens bonded to this across the double bond and only 1 here on this double bond. So the hydrogen is attracted to the one with the most, so it goes to the biggest number, and the halide or the hydroxyl group go to the carbon with the least number. So some memory tips: nothing extra for reactive if it's got a halide. If it's hasn't got a halide, we're going to need a catalyst to help lower the activation energy, so all of these have a catalyst. And if it's got more than 2 atoms, it also needs heat and pressure. So our next lot of reactions are oxidation and reduction reactions. And we focus, when we do the redox unit, on the fact that oxidation is loss of electrons and reduction is gain of electrons. But oxidation can also be classified as the loss of hydrogen or the gain of oxygen. And reduction can also be classified as the gain of hydrogen or the loss of oxygen, which is what we actually see in our organic reactions. So for our reduction reactions, we're adding hydrogen in. So we've already done this, it's sometimes called an addition reaction. So I can have an alkene go to an alkane by adding our hydrogen and a metal catalyst. With a nitrile, I can make it go to an amine through reduction. And what we're doing is we're giving this nitrogen some extra hydrogens and breaking that triple bond. So we'll end up with an NH2, which is our amine. So we can have 2 ways of doing this. We can do the same as we did for our alkene, which is add hydrogen and a metal catalyst. But because it's not a double bond and just adding across, we also will need some heat and pressure in that particular case. Or we can use our lithium aluminium hydride, and we do that with water. It doesn't need the heat and pressure in this particular case. So choose which one, or try and recognize that we have our hydrogens here that we're adding and we have our hydrogens here that we're adding. With oxidation reactions, we need an oxidizing agent. And in the ones that we've learnt about, which is our potassium dichromate and our potassium manganate, they need to be acidified, and they need to be warmed. So we can represent an oxidizing agent as an O with the square brackets around it. And you can see here I've actually put the conditions underneath our arrows. So we'll need the heat and the strong the acidic environment with the oxidizing agent. So primary alcohols, where we have our carbon with the OH on the end, you can see here that with my primary alcohol, when I'm removing this hydrogen, so I remove this hydrogen, I form that double bond, which then forms my aldehyde. That can be oxidized further because I can also remove, actually not remove this, I can add some more oxygen in. So remember, from oxidizing, it can be removal of the hydrogen or adding an oxygen. So here I can add the oxygen in, which then forms our carboxylic acid. So we have our aldehyde and our carboxylic acid able to be formed. Whereas if I have a secondary alcohol, remember with a secondary alcohol, it's coming off a carbon that's in the middle of a chain. And in this case, what we have is that because I'm losing this hydrogen and this hydrogen to form my double bond, well, when I lose this hydrogen and form my double bond, I now have the 4, so I also lose the secondary hydrogen. There's now no longer a hydrogen here, or it doesn't want to bond with any other oxygens. So it can't be oxidized any further. So when we have our ketone, because I've already oxidized it as much as it possibly can with this double bond, and I already have my secondary, it means that I can't oxidize any further. Now, a tertiary alcohol can't actually be oxidized. So we can use the oxidization test as a test for whether it is a tertiary alcohol or whether it's primary or secondary. So remember our colors, with our potassium dichromate, it changes from green to orange, and with our potassium manganate, it changes from purple to pink. So our last set of reactions are our condensation reactions, which are reversible. So the reversible is called a hydrolysis. You'll also have heard of these as esterification reactions, in the particular case of when we make an ester. But both making an amide and an ester are condensation reactions. So in both cases, you'll notice that we require heat. So if you remember condensation, I'm going to need heat. And to do that, we're removing this water. So whenever I do a condensation reaction, it removes water. If I'm doing a hydrolysis, in terms of going back, I'll need to add water to get back to what I originally was. You notice here that where I'm actually taking the water from is from the OH group of the carboxylic acid, and I'm taking a hydrogen off the alcohol or the amine. So that then forms our water, and what's left is what combines. So we'll have our R with our carbonyl group, and we'll have the rest of our amine bonding then to that carbon. As with the alcohol, the remainder of the oxygen from the hydroxyl group will bond to the carbon. In both cases, we have the water produced. If we have an ester forming, we also need a strong acid catalyst. So we don't need a catalyst in the case of condensation of a carboxylic acid and amine to make an amide, but we do to make the ester with the alcohol. And a memory tip that may help you is that ester and catalyst both have ST. So if you remember strong acid catalyst, and you know that it's if you remember that it's an acid catalyst because you're mixing an acid, so it needs an acid catalyst, but the only one that needs it is to make an ester. So that may help you to actually remember. So how do we then use these? So if we remember or we're given a particular product or a particular starting agent, or we might be given an intermediary. And remember that we could potentially have two-step reactions that we've got to be able to do in terms of reaction pathway. So if we've got a desired product, we may not be able to get to it straight away. So I might not be able to get from an alkene to I can't get from an alkene straight to a carboxylic acid. I have to go through multiple pathways to get there. To make an alcohol, I can actually have two different routes. So I can have come from an haloalkane where I would have added sodium hydroxide in water, aqueous, or I could have come from an alkene where I needed that strong acid catalyst. And I also needed water. So both of them needed the water present, but if you were told that it was mixed with sodium hydroxide, you know it has come from a haloalkane. Whereas if you were told that it was mixed with water and an acid catalyst, then you know it's come from an alkene. So remembering what your conditions are helps you actually determine what the product was before, if you're told the product that you end up with in the middle or at the end. For example, the same thing with an amine. An amine can have come from a nitrile or it have come from a haloalkane. So if you were told that it was combined with ammonia, or if you were told that it had hydrogen plus a catalyst, so looking at what the reactants were, if it was an amine, it's an amine that had ammonia in the reactant. It's come from the haloalkane. If you were told it had hydrogen as a reactant, it's come from the nitrile. With our alkanes, we can make our alkanes from our alkenes, or we can make a dihaloalkane. We do need to remember that if its end product is a carboxylic acid, that this would have been a primary alcohol. So if we were told that the intermediary was an alcohol, the final was a carboxylic, and we were trying to work out whether it came from a haloalkane or an alkene, if you've got to say that what the structure of this was, remember that that OH group has to be on the end. Can't be a secondary. Because this has to have been a primary alcohol to go all the way down. You may have to show that this is a reversible reaction, which means that you're going to have to say, if I have an ester plus H2O and I add this acid catalyst plus and add my water in, I'll go back to being my alcohol and my carboxylic acid. So make sure that you can recognize the parts of an ester. So if you were given the formula of an ester, remembering that this part of it, where it was bonded to the single bond O, that will make your alcohol. So this is going to have the R that was here. This will have the OH on the end, and the R that was here is going to have my OH join on. So making sure that you can recognize which part belongs to which and be able to just then add what was added to it on this end. So if it was a CH3, CH2, that's what you put on this end. And if this was a CH3, that's what you put on this end.